Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over the min and max of a function. We're going to start locally and then expand globally. So a local, minimum, and maximum. What exactly do we mean by the term local? Essentially, it means nearby. You can think of it as in the same neighborhood, close, etc. So a local minimum is a point on the function where all the surrounding function values are larger. And a local maximum is a point on some function where all those surrounding function values are smaller. So let's take a look at our graph below. So looking at this first graph I have pictured, we're going to locate the local minimum value. So a point along the function where all other surrounding values are larger than it. This function continues on, so we know that we're not going to have any local minimum that way. But as we continue along the function, what do we get to first? Right here, it looks at roughly the 0.05. This point here is larger than any other surrounding function values, which means that's a local maximum at 0.5. So here we have a local max. Whereas if we continue along our function, this point here, we have points that are greater than it and points that are smaller than it locally. So we'll continue on until we get, look at here. This point here has a smaller function value than any of the other points. And I believe this point is roughly 2, 1. You can see that to the left of that, our function values are greater, and to the right of that, our function values are also greater. So this is known as a local minimum, or a local min. And we continue on increasing further, so we don't have any more maxes or mins. Let's look at this second example. What makes this second example slightly different is now that our function doesn't continue on, we have endpoints, or at least one endpoint over here. We have that open circle. So let's first just look, not at our endpoints, we'll talk about our endpoints in a second, let's look at everything between those points. So you can see that we have a local maximum here, because that's the largest value around. We have, continuing along our function, here is a local min. There's no function values around that are lower, and then up here we again have a local max. So in this case, we have 2 local maxes. And you can have multiple local minimums and multiple local maximums within the same function. And you may also hear the term relative. That's another synonym for local in this case. So a function can have multiple relative maxes and multiple relative minimums. However, now let's go to our endpoints, because one would believe, oh, well right here, this function value at that point is smaller than any other value around it. But because we're cutting our function off and restricting it to an interval, we don't know what the function looks like on this left-hand side. Our function could go up, and then yeah, sure, that would be a local min. But our function could also then continue down, and that endpoint wouldn't actually be a local minimum because points to the left of that are smaller. So with that being said, endpoints, those ends of our intervals, will never be local minimums or maximums. However, which we'll get into in the second half of this worksheet, we'll talk about absolute. Endpoints can be absolutes, but they cannot be local. Now, what we're finding here essentially are critical points. A critical point is a point on the function where the derivative is 0 or the derivative does not exist. And note, well, that point has to be in the domain of the function. But these local maxes and these local minimums are when the derivative is equal to 0. So those are critical points. And again, I want to note that for a critical point, when that derivative is equal to 0, if the x value that makes the derivative 0 was not in our original domain, meaning that it made our function undefined, then we are not able to use that as a critical point. So x needs to be in the domain in order to be a critical point, and then if it is in the domain, if the derivative equals 0 or the derivative doesn't exist, we know we have a critical point. So in example 1, we're going to find all the critical points for the following functions. Again, critical point, we're going to take the derivative and set it equal to 0, or see when the derivative is undefined. So for h of x, taking that derivative, we'll do h prime of x, and I'll go ahead and zoom on in. Taking the derivative h prime of x, that's 4x cubed over 4 plus 3x squared over 3 minus 2x. Simplifying this derivative down, h prime of x is equal to 4 over 4 cancels out, so that's going to be x cubed plus 3 over 3 cancels out, so that's just x squared, and then we have our minus 2x. Now we want to see when this is equal to 0, because since we don't have that rational function, we can plug in whatever x values we want, so there's never going to be an x value that makes our derivative undefined. So our critical points are going to be when that derivative equals 0. And in order to see this, it's going to be fairly easy to factor it. If I pull out an x among my derivative, I'll have x squared plus x minus 2 equals 0. So now, in order to finish factoring, I need to see what multiplies to give me a negative 2 and adds to give me a positive 1. That's going to be positive 2 and negative 1. So my h prime of x, that is going to be completely factored x times x plus 2 times x minus 1, and I'm going to see when that equals 0. And having it factored like this, it's going to be easy to see when this equals 0. It's going to equal 0 when x equals 0. It's going to equal 0 when x equals a negative 2. And it's going to equal 0 when x equals a positive 1. So 0, negative 2, and 1 are my x values where I'm going to have critical points. So let me order this, going from negative to positive. Again, that's negative 2. Our derivative is going to be equal to 0. When x is equal to 0, our derivative is going to be equal to 0. And when x equals 1, our derivative is going to be equal to 0. And at those different points, we're either going to have a relative minimum or a relative maximum. And I'll go ahead and just find those x values. Feel free to take these x values and plug it into our original function to get the full x, y coordinate point. However, I'm just going to write those x values for the sake of time. Now, let's move on to b. So for part b, I have that f of x equals 3 cosine of x, and my interval is from 0 to 2 pi. So finding those critical points when the derivative equals 0, or that derivative is undefined as long as x is in that domain. So taking my derivative, f prime of x, I'm going to have 3 times the derivative of cosine of x, which is negative sine of x. So this is going to be negative 3 sine of x. Now, I know that my domain for sine of x is all real numbers. So there's no x value that's going to make this function undefined. So in order to figure out my critical points, I'm going to set this equal to 0. Dividing both sides by that negative 3, I'm going to see when sine of x is equal to 0. But remember, I have this restriction. 0 to 2 pi is my interval, not including those endpoints, which would not be relative mins or maxes anyway, because they are endpoints. But this unit circle might be helpful to draw out. If I'm going from 0 all the way back around to 2 pi, I need to figure out when sine of x is equal to 0. Well, that's at 0 and 2 pi, but remember again, they're not in our interval, or it's at pi. So in this case, when x is equal to pi, sine of pi is equal to 0, so negative 3 times 0 is 0. At pi, I have that critical point. Which it makes sense too, because if you think about the graph of 3 cosine of x from 0 to 2 pi, cosine at 0 starts at 1, and then we get to pi over 2, it's 0, and then at pi it's at negative 1, 3 pi over 2, it's back to 0, and then finally back up to 2 pi. At pi though, we have that horizontal tangent line. So the derivative is indeed equal to 0. So sometimes it's a good idea just to visualize and draw this out, so that you can tie all your different vocabulary words together to really understand what's happening. But for now, let's continue on. Now we have the extreme value theorem, which we'll go over in a little bit, but we also have something called the local extreme value theorem, which that says that if the function has a local min or max at c and the derivative at c exists, then the derivative of our function at c equals 0. So you can see this graph that I have at the right pictures this local extreme value theorem. So if the function has a local min or max, which it does at point c, I have that highlighted, that c is that minimum, and the derivative exists, then the derivative of our function at c equals 0. So because it's a local min or max and the derivative exists, we know that that horizontal tangent line is going to give us a derivative of 0. Now there's a couple cases where we can have a local min or max at c and the derivative doesn't exist. For example, if you remember back from when we talked about how differentiability implied continuity, but continuity doesn't necessarily imply differentiability, think about if our function had a cusp. We know at that point right there, it's not differentiable. However, it's still that local max, but the derivative does not exist. Therefore, because that derivative doesn't exist, then we know that it can't equal 0. So that's an example of having a local maximum, some critical point that doesn't necessarily make our derivative equal 0. So in order for that local extreme value theorem to be true, to apply, we have to have a local min or max and the derivative has to exist. If both those are the case, then we know that that derivative is 0 at that point. If one of those fails, either we have a local min and the derivative doesn't exist, or the derivative exists and we don't have a local min or max, well then we can't necessarily say that the derivative equals 0. However, if we have a local min and max and the derivative exists, then we can definitely say that that derivative equals 0. Let's continue on to the next page, and on this next page we're going to learn about absolute minimum and absolute maximum values. Now, absolute minimum values and absolute maximum values can exist at endpoints. That's what makes them slightly different than the relative. And also being that they're absolute, or global minimum and global maximum. That's another term. The absolute minimum is smaller than any other point on the function. That's it. So you're only ever going to have at most one absolute minimum. You can have multiple points that have that same absolute minimum value though, but there's only going to be one at most absolute minimum function value. You can have multiple points that have that same value, but it's only going to be that one value. Same with an absolute maximum. It's just larger than any other point on the function. And again, you're going to have at most one absolute maximum value, but that value can have multiple points. So you can have, for example, let me make sure that you can visualize this. If you have some function that looks like this, actually let's go ahead and do the sine function. And I'll just do that simple sine of x. You can see that my absolute maximum, my greatest values are all at the peaks. But that absolute maximum occurs multiple times, however, it only has that one value. And my absolute minimums, same deal. I have multiple x values that represent that absolute minimum, but it's only that one value. And again, this can include endpoints if an interval is defined. So let's look at the first picture. You can see that these are the same exact pictures we had up above. So if you remember, here was a local maximum, here was a local minimum. Where's an absolute max and where's an absolute min? Well, think about it. My function is continuing on all the way towards negative infinity, so I have no absolute min. And my function is continuing on towards positive infinity, so this one I also have no absolute max, because I do not have one point that I can say is greater than all other points. And I don't have some point that I can say that is smaller than all other function values. But let's look at this next one. This next picture, remember we had relative maximums at these 2 points and a relative or local minimum at this point here. What is my absolute max? what value is greater than all other values? That's this point right here. I have one absolute maximum. And which point is smaller than all other values? This point here. That is my absolute minimum. But let's continue on to example 2. In example 2, we're going to locate all the relative and absolute minima and maxima for each of the following. So let's start with this first picture looking for the relatives. Remember, the relative or local minimum and maximum cannot be endpoints. So I know that this point here is a local max, and I know that this point here is a local min. And these are my endpoints, but my endpoints cannot be local. Now let's talk about absolute. And in this case, I'll be able to find an absolute minimum and an absolute maximum. A point on my function that is smaller than any other function value is this right here. That is my absolute minimum. And a point that is greater than any other point on my function is up here at this other endpoint. That is my absolute maximum. So in this case, I had one local max, one local min, one absolute max, and one absolute minimum. So a relative min and max, and a global max and min. Now I want to note, think about this. What if we didn't have this endpoint filled in and it was just some open circle? Well, if it was just some open circle, then we would not have an absolute max for this problem. Because what is that value that is the greatest value? Let's pretend that this is roughly, let's say 6 in the y. What exactly is that absolute maximum? Is it 5.9, 5.99, 5.999, 5.9999? You see how we can't definitively say exactly what that value is? So in this case, we would have no absolute maximum. However, if that point is defined, we know that there's nothing greater than that value of 6, so we would. So back to the original, we do have that absolute maximum, but if that endpoint wasn't defined, then we would have no absolute maximum. So overall, no absolute maximum for our function. Let's move on to our next picture, and this one I'll put my arrows, continues on. So I have a relative maximum. In other words, a local max at the point 0, 5. Do I have any local or relative minimums? No, because the function continues on towards negative infinity. And also because the function continues on towards negative infinity on both sides, I have, not only do I have no local min, but I also have no absolute minimum. However, I do have an absolute max, and that absolute max is where my relative or local max occurs. That's where my absolute or my global maximum also occurs, at that same exact point. So relative and absolutes can occur at that same point. It's both a relative and an absolute. It's both a local and a global max. They can occur at the same point. So now let's continue on where we're not looking necessarily at a graph, we're going to be looking at functions. So for example 3, it says to find all the relative or local and all the absolute max and mins for the following function. And because we have some interval where the endpoints are included, we're going to need to double check those values for our absolutes. But to find the relative, we're going to take the derivative and set it equal to 0. So f prime of x, when I take that derivative of x squared plus 4, that's going to be 2x plus 0. And when does the derivative 2x equal 0? That's when x equals 0. So x equals 0, I'm going to have a critical point. And that's probably either going to be a relative maxima or a relative minimum. I need to decide what it is. And eventually, we're going to figure out how to do that using the second derivative, that next higher order derivative. But for now, since we haven't really touched on it, let's just think logically about this. I have x squared plus 4. That parabola is a parabola that opens up and has an intercept at 4. When I have x equal to 0, that's going to be a what? A minima. So the point 0, 4 is a relative or local minimum. But if you look, even if my function continued on, I know in this case it doesn't, but that's the most minimum value we have for our function, so it's both a relative and absolute minimum. Now, because we stopped this at -2 and 2, I know my function does not continue on, so I'll go ahead and erase those arrows, and those points are included. So here would be -2, and here would be 2. I have to figure out if one of those is an absolute max, because I know they're not going to be an absolute min because my x equals 0 is already my absolute min. So how I figure that out is I plug -2 into my original function. So when x equals -2, or when x equals 2, what value am I going to get? -2 squared is going to be a positive 4. 4 plus 4 is 8. And 2 squared is 4. 4 plus 4 is 8. So at both of those, I have an absolute maximum. Remember, endpoints cannot be relative maximums, but because they have the same value and those are the highest values on my entire function, I have an absolute maximum when my function value is equal to 8, and that occurs at two different places, -2 and 2. Let's continue on to part B. In part B, I have that g of x equals x cubed over 3 plus 3x squared over 2, and I'm going from -4 to a positive 2. So taking the derivative, g prime of x, that's going to be bringing the 3 down in front, 3x squared over 3 becomes x squared, plus if I have 3x squared over 2, bringing that 2 down, this is just going to be a 3x. So the derivative of g of x, g prime of x, is equal to x squared plus 3x. Now I need to find my critical points for this function in order to figure out when my derivative is equal to 0. Because in this case, my derivative is never undefined. So rewriting this, factoring it, I'm going to pull out an x, so this is going to be x times x plus 3, and I'm going to set that equal to 0. So my two separate x values are going to be x equals 0 and x equals a -3. At those 2 points, I'm going to have either a relative maximum or a relative minimum. I just don't know which one is a relative max and which one's a relative min, but I'm going to figure that out. And then also I have to test my endpoints. So first, let's figure out what my function values are when x is 0 and when x is -3. When x is 0, plugging 0 in for x, I'm going to get 0 for y. And when x is -3, if I plug -3 in, I would get -3 cubed over 3 plus 3 times -3 squared over 2. -3 cubed is a -27, but if I'm dividing that by 3, that's going to be a -9, and then I'll add that to 3 times -3 squared is 3 times 9, which is 27, so that's 27 over 2. So -9 plus 27 over 2. If I was to combine those, I'll write -9 as -18 over 2. And 27 minus 18 is a positive 9. So 9 halves. So at -3 in the x, I'm at 9 halves in the y. That's either a relative minimum or a relative maximum. I think we're going to need a little bit more information before we make that call. So I'm going to leave those points as is. So now I'm going to plug in my endpoints. So I'm going to plug in -4, and then I'm going to plug in 2 to see what values I get for my function. If I plug in -4, I'll get -4 cubed over 3, which is going to be -64 over 3. And then I'm going to be adding that to -4 squared is 16. 16 times 3 is 48. 48 over 2 is 24. So finding that common denominator, that's going to be a common denominator of 3. So rewriting 24 in terms of thirds, that's going to be 72 thirds. So when I combine these together, 72 minus 64 is going to give me 8. So this is going to be 8 thirds when I'm at a value of -4. And then lastly, I'm going to figure out what happens when I plug in 2. 2 cubed is 8, so that's going to be 8 thirds, plus 2 squared is 4. 3 times 4 is 12. 12 divided by 2 is 6. So I have 8 thirds plus 6. If I find that common denominator of 3, that's going to be 18 thirds plus 8 thirds, which gives me 26 thirds. Now the easiest to find are going to be my absolute maximums and absolute minimums. And remember, I'm going to make a note that these are endpoints. So these definitely cannot be relative. They can only potentially be absolute maximums or absolute minimums. And if I look at all my y values, which one is the smallest? Well, all of these are positive except this one's 0. So this is my absolute minimum. And which is the greatest? That's going to be my 26 thirds. So that is my absolute maximum. So this endpoint is nothing. This -4, 8 thirds is not relative or local because it's an endpoint, and it's not an absolute because I've already decided my absolutes. Now, my last step is to figure out which of these are relative maxes or minimums. And if this is my absolute minimum, we know that that is lower than any other function value, so that's also going to correlate with a relative minimum or a local minimum. So I'm going to write relative minimum, and then that means that this is going to be if my function is continuous and I have a relative minimum at 0, 0, when I'm at -3, if that's greater than that 0, 0 value, my function was continuing upwards, that's going to be a relative max. So there we have it. My absolute min and relative min are the point 0, 0. My relative or local max is the point -3, 9/2, and my absolute max occurs at the point 2, 26 thirds. And again, like I mentioned earlier, this is going to be a lot easier when we learn about taking the second derivative. Eventually, I'm going to introduce you to that next higher order derivative, the second derivative, and what that means about the original function. Once we figure that out, deciding whether these are relative max or mins is going to be significantly easier, because then we don't have to look at those surrounding point values to figure it out. We'll know directly at that point based on the sign of that second derivative, which we'll learn in the next couple of example videos. But for now, let's continue on. Just as there is a local extreme value theorem, there is an extreme value theorem. What the extreme value theorem says is that as long as we're on a closed interval, a continuous function contains both an absolute maximum and an absolute minimum, what I have pictured here. I could also have a closed interval where I have some endpoint here, and my function looks like this. But even though my absolute maximum and minimum don't occur at the endpoints, they exist. But this is not the case if, for example, we had some function. I'll draw this same exact function that I have pictured, but let's pretend that our interval is not closed. Well, then we do not have an absolute maximum in this case because we don't know what that value is. But if the interval is closed, then we have both an absolute maximum and an absolute minimum. It doesn't have to be at that end point, but we are guaranteed to have one of both. So that's just something to think about, and we can relate this directly up above. In example 3, both of our functions were on a closed interval, and our functions were continuous along that interval, and you can see that in both, we did indeed get an absolute minimum and an absolute maximum in each case. So the extreme value theorem is a good double check for figuring out if you even potentially have an absolute min or max, or that global min or max. But with that, we wrap up this example worksheet of learning about local or relative mins and maxes, and global or absolute mins and maxes. Continue on to the next video where we're going to learn another theorem, the mean value theorem. So stay tuned and continue on. But until then, good luck with your online learning.